All right, so now that we took a look at sampling distributions of sample means, let's just take a look at the difference between how do we know when it's a sampling distribution of sample means and how do we know when it's just a regular old problem like we did way back in like chapter 2. Okay, so let's start with this question. Then we're going to look at two different scenarios to show how we can decide when we're dealing with sampling means and when we're not. So the height of young women follows a normal distribution with mean, now note that that's the population mean, 64.5 inches, and standard deviation, population standard deviation of 2.5 inches. Let's take a look at this question. This says, find the probability that a randomly selected young woman is taller than 66.5 inches. Okay, now you should read this and say, find the probability that a randomly selected young woman is taller than 66.5 inches. Since this is just talking about one randomly selected young woman, we should recognize that that's just like a regular old question like that we've done in the past, okay, because when we take a look at this example right here, this is saying the height of all young women. So this is a population distribution. This is all individual women. They took all of the women, put them in a distribution, all individual values, and the mean of all those individual values was 64.5, and the standard deviation of all those individual values was 2.5. So therefore, this is just following the types of questions that we did back in chapter 2. Okay. So this is the same thing we've done. We're defining the random variable, calculating the probability, draw a picture, use z-scores, answer in context. So we're just doing the probability that x is greater than 66.5. Okay, so that's, and I'm saying we're using x because x stands for one individual woman. Okay, now notice how this question 2 is different. Find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches. Now, since this says simple random sample of 10 young women, that's saying the whole sample of 10 young women exceeds 66.5. So this is saying when I take a simple random sample of 10 young women and I find the mean, what is the probability that if I pull one of those simple random samples of 10 young women out, that the mean of that sample is going to be greater than 66.5? Then you should say, okay, wait a second. So since I'm looking at a mean of 10 young women, I should know that that's a sampling distribution of sample means, okay? And I'm going to have to find the new mean and the new standard deviation that go along with that. Okay, so here's how you can do this one. This one you have to check the conditions, okay? What are your conditions? Is it a simple random sample? Yep, simple random sample. Is it approximately normally distributed? Well, 10 young women doesn't meet the CLTO, but the original distribution is approximately normally distributed. Good to go. And is it independent? So there are definitely more than 10 times 10 or 100 young women. Now, you're going to find the mean and the standard deviation for the sampling distribution. So the mean is the same as the mean of the population. Remember, the standard deviation is the standard deviation of the population divided by the square root of 10. Okay, because since we're taking averages, the variability is going to decrease from the original population distribution. Then you're going to calculate the probability just like you did in question 1. Find the probability that x bar, so this is different, x bar is greater than 66.5. Why x bar instead of x? Well, x bar is telling us that I'm looking at a mean of young women. Just when we say probability to x, that's one individual, okay? So I just wanted to go over the difference between questions 1 and 2, and then we're going to go over how to do something like question 2. Okay. So let's take a look at question 1. I kind of already went over that. Now notice, let x equal the height of a selected young woman. Here's x being normally distributed. You always want to state approximately normally distributed, mean, standard deviation. Now, here's your z-score, okay, minus the mean divided by standard deviation. Notice how my probability statements, the probability that x is greater than 66.5. That's important because that x here is showing x is one individual woman, picking one woman that her height is greater than 66.5. Okay, then the probability that z is greater than 0.8. Okay, use your graphing calculator to get 0.2119. So probability of choosing a young woman at random whose height exceeds 66.5 inches is only 21%. Okay, now this is not a sampling distribution. We're looking at the mean height of one randomly selected woman, just one. Okay, so make sure you read the questions carefully and your notation is careful. Okay, so with the second one, okay, this one is a sampling distribution because we're checking to see if we have a simple random sample of 10 young women, the mean of that one particular sample is greater than 66.5. Once you recognize that, you have to check these conditions, because if we can't show that it's normal and we can't show that it's an unbiased situation and we can't show it's independent, then we can't use the normal approximation. Okay, we have a simple random sample. There's more than 10 young women in the population. That's my independence. And the sampling distribution of sample means is approximately normal since the population is normal. So this sampling distribution is going to be taking 10 young women, finding the mean, putting it on the curve. Taking another 10 young women, finding the mean, put it on the curve. Another 10 young women, finding the mean, putting it on the curve. Okay, over and over again. Now, the mean of X bar, notice your notation. The mean of that sampling distribution is the same as the population mean, which is 64.5. Okay, however, the spread is going to be smaller because I'm taking averages. I'm averaging those high and low values. The standard deviation, notice, of X bar, okay, is the standard deviation of the population divided by the square root of the sample size. 0.79 is much smaller than 2.5, but notice the notation, standard deviation of X bar, that's showing us that we're looking at a sampling distribution, not a population. Approximately normally distributed, 64.5, 0.79, make sure to include that. Finding my z-score, notice how I'm using the new standard deviation. Now, notice this difference right here, probability that X bar is greater than 66.5. That was different than the previous one. The previous one just said the probability of X. X bar is telling us, hey, we are looking at sample means. I'm looking at a mean. We want the mean of a group of 10 women to be greater than 66.5, okay? That's a much smaller chance when you do that calculation. It's very unlikely, basically less than a 1% chance, that when we choose a simple random sample of 10 young women, their average height is going to be greater than 66.5. I just want you to understand that it's like taking one of the sample means out of your distribution and checking to see if that one sample mean has a height of greater than 66.5. Okay, just make sure you read your questions carefully and understanding when you're dealing with sampling distributions and sample means. Okay, so what I want you guys to do is go ahead and take a minute, read this question, try it, and then take a look at the answer on the next page. Okay, so just make sure you've read it carefully. Are they asking for the probability of a single sample, sample proportions, or sample means? Hopefully you read this and you said, okay, wait a second. When I said the mean is an hour and standard deviation is 1, that's the whole population. That's individual values. But they're taking a simple random sample of 70 air conditioner units in the city. Okay, since I'm taking 70 and finding the mean, that's going to be a sample mean, okay? And it's averages, not sample proportions, okay? Just make sure when you're doing your answer, you're checking your conditions, you're calculating the sampling distribution, mean and standard deviation, and then you're calculating the probability like you've done in the past. Okay, number 1, check your conditions. We have a simple random sample. That's going to allow it to be unbiased. There's most likely more than 700 air conditioners, therefore it's independent. Make sure you show that in context. The sampling distribution will be large enough. 70 is greater than or equal to 30 by the central limit theorem, so therefore the distribution will be approximately normal. Make sure you state central limit theorem, sampling distribution approximately normal. Now, mean of the sampling distribution is the same as the mean of the population equal to 1. Standard deviation, here's your work for it. Okay, so we know it's approximately normally distributed. Now notice the notation. The probability that a group, okay, of 70 air conditioners is greater than 1.1 hours. The average of the 70 air conditioners, okay, that the mean time is greater than 1.1. Okay, notice I'm using the standard deviation from my sampling distribution, probability of the z-score, and then your final answer. Okay, so each one of these, think of these as little x bars, pulling one of the x bars out, and if I'm taking one of those x bars, the average of that x bar is greater than 1.1. Okay, if you budget 1.1 hours per unit, there's a 20.33 chance that the technicians will not complete the work within the budgeted time. Okay, so then I guess the tricky part about this was you've budgeted an average maintenance time of 1.1 hours. Is that going to be enough? So that was tricky in understanding that, okay, is that going to be enough? You're basically finding the probability that it's more than that, and if it's more than that, then you haven't budgeted enough time. Okay, so go ahead and try this one. Okay, this one was a little bit trickier, okay? So we have our population mean, population standard deviation. You have a simple random sample of 50 students that have an average of 25,000 texts per day. So that's the tricky part. So that's saying that the 50 students together have an average of 25,000 texts per day. But keep in mind that that's all all the students, okay? All of them together. We want to know what is the average group of 50 students. So each group of 50 students is only sending 50 texts per day. So this is the individual, okay? So if I was going to take all 50 students, okay, and add up all of their texts and then divide by 50 to find out the number of texts per student, that's going to be the 50 texts per day. Here, this wording is tricky. 50 students have an average of 25,000 texts per day. So that means 50 students, total of 25,000 texts per day. We want the mean of 50 students, so the mean of an individual student. So that's why I have to divide by 50 here. So that definitely was a little bit trickier. Okay, we have a simple random sample of 50 students. There's most likely more than 500 students in the school. Make sure you show this work and in context. Make sure you state it's independent. By the central limit theorem, it's approximately normal since 50 is greater than 30. Remember how it said that originally the population was right skewed? So you couldn't do normal calculations on this unless the central limit theorem applied. Okay? New mean, new standard deviation, note the notation, x bar, x bar. Now, notice how this says the probability that x bar is greater than 50. That 50 came from this part right here, okay, because we're checking to see what is the probability that when I choose a group of 50 students, that the average of those 50 students is 50 texts per day. Okay, so that came from this portion down here. That was a little bit tricky. Okay, found your z-score, probability that your z-score, okay, there's a 15.62 chance that a random sample of 50 students have sent over 2,500 texts per day. Okay, all right, go ahead and try this one. See if you can figure it out based on what you've learned. Okay, so this one is a little bit different because it's saying how many axles would you need to sample if you wanted the standard deviation for the sampling distribution of sample means to be 0.0005 millimeters. When it says justify your answer, that means show your work. Okay, so here's what you know. The grinding machine in an auto parts plant prepares axles with a target diameter, the mean of the population, standard deviation of the population. But we're taking a look at the sampling distribution. How many samples do I need to take in my sampling distribution to make sure the standard deviation is only 0.005? So we know the formula for a sampling distribution, okay, is the standard deviation divided by the square root of n. Fill in what you know. We know what we want it to be. We know that the population is 0.002. We don't know what the square root of n is. So just rearranging, I'm multiplying the square root of n, putting it over here, dividing by 0.005. Okay, so I get this. So square root of n is equal to 4. When I divide these two together, square both sides, you get n is equal to 16. Okay, so this is just a quick summary of what we've done. We found the mean and standard deviation of the sampling distribution. Make sure you calculate the 10% condition, population's 10 times the sample size, before you use the standard deviation. Explain how the shape of the sampling distribution is affected by the shape of the population and the sample size. Remember, the central limit theorem tells us nothing about the variability. Okay, the sample size tells us whether or not the standard deviation is big or smaller. And then when appropriate, use the normal condition to calculate probabilities involving sample means.